Hi everyone. So today we are looking at properties of integrals, and honestly I think a lot of these are going to feel like common sense to you. I did post this page separately so you could fill these out before we start talking. I mean, you're welcome to try to write them in as we go, but I filled them out ahead of time so that we didn't have to spend so much time just doing the writing. So if you would like to pause the video at this time and write all of this stuff in or go access the file that's posted, you're welcome to. So remember that when we're talking about integrals, all of these, everything you see here on this page, what we're really talking about is the area under a curve, right? So we say like from A to B, we're trying to find this area underneath here, okay? So it's important to kind of just keep that in mind as we're working through this. So this first one is talking about the order of integration. And so the way I wrote this, the A is first followed by the B, right? The A is further to the left. And so that's usually how we would think about integrating, is starting at A and going to B. If I take those endpoints and reverse them, so if I say I want to integrate, but I want to start at B and go backwards to A, what that does is negate this value. Because if you think about, like, this is accumulation, right? If this was like population growth here in this function, then integrating from A to B would tell me how much the function has increased between time A and time B. If I integrate backwards, what that's telling me is how much the population would shrink if I went back in time, right? So that would be like, if I went from B down to A, I would expect that my population would have shrunk by this much. So when you switch the order of the boundaries, your integral turns negative. That's what this first one's talking about. Second one should also be sort of common sense. If you integrate from A to A, so you never leave this point, right? Your boundary doesn't have anything in it. That's always just going to be equal to 0. Okay, so anytime these two numbers are exactly the same, the integral is 0 because there's literally no area between A and A. Okay, constant multiple. This one's a little bit harder to see using my pretty picture here, but this is similar to when we did derivatives. If you're doing the integral of a function that has a number in front of it, so let's say, for example, this was a 3x squared, you are allowed to do the integral of the x squared and then just multiply by 3. You can pull that constant off of there. That's a trick we're going to use a lot. It's a trick we used a lot with derivatives, that if there's a number sitting in front of your function, you can kind of just save it for the end. Okay, sum and difference. This is really just saying that if you're trying to do the integral of two functions that are being added or subtracted with each other, you're allowed to do the integral of each one separately and add and subtract the integrals. Again, I don't really have a picture to represent that because I'd have to draw two functions. But this, again, is similar to derivatives, is that with derivatives, you could do the derivatives of each piece and add them together. Same thing with integrals. You can integrate f of x, you can integrate g of x, and then just add together or subtract the areas. The additivity one sounds a lot like sum and difference, but it's a little bit different. If you really look at it, I think you can make it make sense to yourself. But what this is saying is that if I have an area from A to B, and I add that to the area from B to C. So notice that like this endpoint and this endpoint are exactly the same. That's the same thing as just doing the area from A all the way to C. So in my picture, C would be something like this over here. And so what we're saying is, if I want to take the area from A to B and add it to the area from B to C, that's really the same thing as just doing the total area from A to C. Okay? We can also use these, so like if I knew this area and I knew this area, I could do some subtraction to figure out this area. So that's a kind of trick that we use quite a bit. The one of these that I think is probably the hardest is this one, the constant rule. So if you are integrating something that is just a number, okay, this is different than a constant multiple, but it's just a number, the answer is not just that number. And it's also not just 0, which is what it was when we were talking about derivatives. Okay, the answer is the number times the width of the interval. And I want to show you why. So if the thing I'm integrating is a constant, then what that graph would look like is just a horizontal line at k, right? And what we're really trying to find here is the area under this line between A and B. Okay, so we're trying to find the area of essentially a rectangle here. So the height of that rectangle is k, because that's how high up this line is. But the width of that rectangle would be b minus a. So remember that when you're doing this, this is talking about an area underneath k. And so it's not just going to be k, it's k times the width of the interval. So when we get to one of those, I'll make sure I talk about that in more detail, you know, with a specific example. But that constant one does tend to be the one that sneaks up on people. Okay, so let's do a couple of examples here. And I do realize that we don't quite know yet how to actually calculate these integrals. For all of these examples, we're kind of assuming that we just know the integrals already. So we know an integral of f of x from negative 1 to 1, that has an area of 5. From 1 to 4 is negative 2. And then do pay attention to the fact that this is a different function. This is h of x from negative 1 to 1, and that area is 7. And we're just going to apply those properties to answer all of these questions. So, for example, the integral from 4 to 1, you'll notice that here the integral from 1 to 4 is negative 2. This is just the same thing but with the endpoints reversed. So I would say that this is negative 2, or in other words, just positive 2. Okay, if I want the area all the way from negative 1 to 4, notice that this one goes from negative 1 to 1, and this one goes from 1 to 4. So if I want to go all the way from negative 1 to 4, all I have to do is add these two things together. So it's 5 plus negative 2, which is 3. Okay. For this one, my integral is going from negative 1 to 1, but notice I'm using the f function and the h function. So I'm going to be talking about these values here, because these go from negative 1 to 1. And then with the 2 and the 3, I'm just going to use my constant multiple rule. Okay? So let me write out what I'm doing here. I don't think you would really need to write this all out this way to be able to answer this question, but maybe for the sake of your notes, it would be helpful. What I'm going to end up doing is 2 times the integral of f of x plus, it's coming from right here, 3 times the integral of h of x. So I pulled the 2 and the 3 out using the constant multiple rule, and I separated into 2 separate integrals using the addition and subtraction rule, or the sum difference rule. I forgot what it was called. But so I'm just going to go 2 times this integral, which from up here is 5, plus 3 times this integral, which is 7. And so I have 10 plus 21, so I would say my answer here is 31. Okay, this next one is a trick question. This next one wants you to go from 0 to 1. And I don't have anything that includes a 0, right? I do have from negative 1 to 1. And this is technically like halfway between negative 1 and 1. So this is essentially like splitting that area. And so what I see a lot of people do with questions like this is they want to just say, oh, we can just cut that 5 in half. But we don't know that this area is symmetrical. I mean, even just using this picture we were using a second ago, if I was looking at it from negative 1 to 1, right, and I was looking at this area, I can't say that this area is exactly half and this area is exactly half, right? If it's not symmetrical, then these two areas might not be the same, so I can't just take the total area and split it in half. So based on the information we have, we can't answer this question. I would just say, you know, not enough information, It's not that there's no solution, but without knowing more about these functions, I can't answer it with the information that I'm given. So don't fall for that trap where you think that you can just split the integral in half. Okay? Okay, kind of the same thing with this next one. I know from -1 to 1, so now it suddenly wants me to go from -2 to 2. I don't have enough information for that either. It's not just double, right? I mean, technically what I'm doing is taking this interval and just pulling it out on either side. But there's no way of knowing if the area that I have here is just going to continue in the same direction when I pull out to -2 and 2. So this is another one that I would say not enough info. Okay, there's no property that would tell me how this relates to this. This one should work though. From -1 to 1, honestly, this one is like a less complicated version of this one, really. I can just take these two integrals from -1 to 1 and add them together. So this is just going to be 5 plus 7. Okay. Now this one, from -1 to 4 of f of x plus h of x, that's going to be a problem. So I could do this, right? I could do -1 to 4 because I could go from -1 to 1 and from 1 to 4. So I technically already have that up here. This piece is 3. But I don't have enough information to take h of x all the way out to 4. And the only thing I know about h of x is this interval here. So this is another not enough information. I just don't want you to fall for the trick questions. Okay, this piece would be fine. This piece is not. And this last one. Okay, so I'm going to split this up a little bit. I'm going to say we're going to do the integral from -1 to 4 of f of x, which we actually already did above, so I'm going to steal my answer from up there. But then we want to make sure that we integrate the 3. We're not just adding 3 to our total, okay? Now, if that plus 3 was on the other side of the dx, then that's what that would be saying, is that you would just find this interval and add 3 to it, which is the mistake I see that happens most often. But we have to make sure that we're integrating that 3 from -1 to 4, okay? So like I said, this is up here in the I think it's the second example here, from -1 to 4. We already know that that area is 3, okay? For this one here, I want to go off to the side and draw a picture of this, kind of similar to the one I did a second ago. So here's my graph. I'm graphing the function y equals 3. So this thing is at 3. And I'm integrating that. Whoops, I'm going to need the left side of my graph here. I'm going to need this to keep going. From -1 to 4. So what I'm really saying is, how big is this rectangle? What is that area? Well, the height of that rectangle is going to be 3. And the base of that rectangle from -1 to 4 is going to be 5. So this is really 3 times 5. And again, that 5 came from the width of the interval here, which is 18. Okay. But what I see people do with this all the time is they want to just find this answer and they say, okay, that's 3, and then they just want to add 3 to that. This 3 gets its own integral, right? We can do an area calculation with that thing. So, okay, that should be enough examples to get you going on the homework for tonight. We'll definitely, there's an infinite number of combinations of these types of problems that we could work through, so you'll definitely run into some stuff that maybe isn't represented here exactly, but you should be able to use the properties to answer the questions. And anything that you're struggling with, I'm sure we'll be talking about. Have a great night.